Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will talk about rho square, meaning the correlation coefficient square. Of course, in the context of simple linear regression. Okay, so we have already shown, right? Let me just write that down. We have already shown that when we consider the following model, and we have y equals beta 0 plus beta 1 x plus epsilon, and where the assumptions were that epsilon had a normal distribution, mean 0 variance sigma square, on the other hand, x was assumed to be normally distributed with its own mean, mu sub x, and its own variance sigma square sub x. Right, furthermore, we assumed that epsilon and x were independent. So what we showed is we derived the mean of the random variable y. It wasn't hard, just from our assumptions, right? What we said is it was something like this, but instead of x we will have the mean of the random variable x. We also derived the variance of y, which is going to be also a nice expression. In this case it's going to be given just by beta 1 squared times sigma square sub x plus sigma square. Okay, and moreover, in another video what we showed was that rho, the correlation coefficient between x and y, is given by beta 1 times sigma sub x divided by sigma sub y. Okay, so let me just write that down here. Beta 1 sigma sub x divided by sigma sub y. Okay, we have already shown that in another video. Okay, so from this, right, we could solve for beta 1. Okay, that's going to be useful, you'll see. solving for beta 1, we have just, beta 1 is going to be equal to rho times sigma sub y divided by sigma sub x. Make sense? Okay, so let me write that down. So we're going to have that guy here. This guy, let me place it here, and this will be now sub y, this will be sub x. Make sense? Again, we're just solving for beta 1. Okay, so now the expressions that we're going to be using in this video are this guy. So this one was the let's call it number 1. This guy, let's call it number 2. And yeah, let's call this one number 3. Okay, so what we're going to be using here are expressions 2 and 3. Okay, those guys are going to be the important ones, 2 and 3. So from 2 and 3, right, what I'm going to be doing here is just plugging in the value of beta 1 in terms of the correlation coefficient and the standard deviations of x and y. Okay, that's what I'm going to be doing. So let me say that here. From 2 and 3, what we have is that the variance of y, which is this, will be the same as, now what I'm going to have is this expression squared instead of our beta 1. Okay, times the variance of x plus variance of epsilon, sigma square. Okay, makes sense? Okay, and this one should be square, right? It's just this guy here. For some reason the square was missing when I copied and pasted. Okay, so now note that sigma sub x square is going to cancel out here, right? So what we're going to have is just rho square times sigma sub y square. Rho square sigma sub y square plus sigma square. Okay, so now that's the expression that we have for the variance of y. Okay. Now note that if we divide both sides of this expression by the variance of y, sigma square sub y, right, we end up with this. Let me just say that. Dividing by variance of y, what we end up with here would be a 1, right? Rho square. And now I have to divide sigma by the variance of y. Okay? Now that is equivalent to just saying rho square equals 1 minus sigma square divided by the variance of y, right? So finally, rho square equals 1 minus this guy. Guys agree? Okay. Now a few observations about that quantity, and those observations will be important. Observations about the square of rho. Number 1. Note, right, from what we did before. If rho is 0, then beta 1 is going to be 0. And on the other hand, if beta 1 is 0, rho is 0. Okay? So there is a correspondence between these two guys. Beta 1, let me just write it down here. Observation number 2. Remember that we have an expression for the variance of y, right? Just from what we had before, from our model, right? Once you find the variance of y, it's given by this, right? And note that it's the sum of two non-negative terms, right? This variance is non-negative, beta 1 square is non-negative, right? So the variance of y is greater or equal to sigma square, the variance of those random fluctuations, right? So let me just say that, and I will copy paste this. It could be useful, it will be useful. So we have from that expression that relationship between those variances. The variance of y is greater or equal to the variance of the epsilon term, okay, which implies that 1, the ratio between them is meaning sigma squared divided by the variance of y is going to be greater or equal to 1, right? But note, rho square is equal to 1 minus sigma square divided by sigma sub y square, right? Which means that rho square is always less than or equal to 1, right? Because this guy here is always less than or equal to 1, okay? So that implies that rho square is always less than or equal to 1. Another important observation here, right, is that, well, since this guy rho square is less than or equal to 1, that means that this guy rho is always a number between -1 and 1, right? You take the square root and that's what you end up with, a number between -1 and 1. Okay, so now let me move to the next observation. When is this guy going to be 1? The only way that rho square can be 1 is when sigma square equals 0, right? And that happens only since this guy represents the variance of those random fluctuations. If the variance is 0, that means that you have no error, right? So, and when that happens, that means that this relationship is exact. So rho equals plus minus 1 only when sigma square equals 0, and in that case you have a perfect linear relationship. So rho is going to be equal to 1 or -1 only when sigma square equals 0, and in that case you have no error, right? And then you have a perfect linear relationship. Okay, so let's summarize what we have done here. We obtained a quantity that is related to the correlation coefficient. We talked about the square of the correlation coefficient. We also talked about some of its properties, and these properties will be important because it turns out that this guy, right, measures the strength of a linear association, right? And the closer this guy rho is to 1 or -1, the closer you are going to be to having a perfect linear relationship. Okay, so we will see in another video how rho square will be useful to come up with a measure of the strength of a linear association in the context of simple linear regressions. Okay, so that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.